Ever stood at the edge of harbor and watched a ship the size of a city block get nudged sideways into a dock by a boat that looks like it belongs in the bathtub? Today we are breaking down exactly what tugboats, how they work. After this video, you'll never look at the harbor the same way again, because what looks like a small boat helping a big one is actually one of the most impressive engineering stories in the world of machines. Let's start with the scale. Really, let's start with it, because until you understand the numbers, nothing else makes sense. A fully loaded Maersk Triple E class container ship, one of the largest cargo vessels ever built, has a maximum displacement of 220,000 metric tons. That is roughly the equivalent of 200,000 family cars, all loaded onto a single floating object moving through the water. At cruising speed in the open ocean, that ship takes about 3 minutes to come to a complete stop. 3 minutes.
Miles.
From the moment the engine is cut to the moment the ship is still. You could fit 5 Eiffel Towers end to end in that stopping distance. And when the ship needs to turn into a port, slide sideways into a berth, or thread through a channel barely wider than its own hull, it cannot do that alone. Not even close. Here is why. A ship's rudder only works when water is flowing past it. Water only flows past it when the ship is moving forward. Slow the ship down at docking speed, which is barely faster than walking pace, and the rudder becomes almost completely useless. At low speed, a vessel that weighs more than 200,000 tons has almost no ability to steer itself. It is essentially a 200,000 ton log drifting on current. That is where the tugboat comes in. A harbor tugboat looks completely ordinary from the outside. Squat, wide, low to water. Most of them run between 20 to 40 meters long. Some weigh as little as 300 tons. So when a 300-ton tugboat pushes a 200,000 ton container ship, it is operating at a size ratio of roughly 1 to 660. That is like a Lambarder trying to steer a Boeing 747 down a hallway. And somehow it works. The reason it works is not brute strength in the traditional sense. It's something called bollard pull. Bollard pull is the true measure of a tugboat's force. It is measured by tying a tugboat to a fixed steel post, a bollard with a cable, and measuring the tension in that cable at full engine power. A large modern harbor tug can generate a bollard pull between 80 and 100 metric tons of force. Some of the most powerful ocean-going tugs in the world produce over 300 metric tons of bollard pull. Now here is what makes the number remarkable. The tugboat does not need to be bigger than the ship. It only needs to apply the force at the right point, in the right direction, at the right moment. Think about a door. A door can weigh 100 kg, but a child can push it closed easily as long as they push the handle end and not the hinge end. The distance from the pivot point multiples the effectiveness of the force dramatically. That distance is what lets a small push do a big job. A tugboat applies the same principle to a ship. Push or pull at the bow or the stern, the front or the back, and even a relatively small force creates an enormous turning effect on the hull. That turning effect is called torque. It is the real reason a small tugboat can rotate something 600 times its own mass, but torque alone is only part of the story, because the direction of that force matters just as much as the magnitude. This is where the engineering inside a modern tugboat becomes genuinely brilliant. Classic tugboats used fixed propellers and a rudder just like a ship. They had to maneuver themselves into position before they could do useful work that took time. And in a busy harbor, time is one of the things nobody has. Modern tugboats use a completely different system called an azimuthing thruster, or in the industry, a Z-drive. Instead of a fixed propeller at the stern, a Z-drive mounts the propeller on a pod that can rotate a full 360 degrees. The propeller can point in any direction at all without the tugboat itself having to change its heading. The result is a machine that can move sideways. It can spin on its own axis. It can push hard in one direction, moving in completely different direction. It can generate thrust forward, backward, sideways, or at any angle in between instantly. A modern azimuthing tug does not need to turn around to push in different directions. It simply rotates its thruster pods and the force changes immediately. Imagine if your car's wheel could point in any direction independently of which the way car was facing, and you begin to get a sense of how free modern tug moves in the water. Now, here is where common sense down completely. This is the part most people never expect. The single most important thing a tugboat does during docking operation is not push the ship forward. It is not guide the bow around a corner. It is not nudge the hull sideways into the berth. The most important thing a tugboat does is act as a brake. Think about a ship again. 200,000 tons moving at barely 2 knots, roughly 4 kilometers per hour. That sounds slow, and it is slow. But the kinetic energy of 200,000 tons moving at 2 knots is still absolutely enormous. Far more energy than anything on the dock can absorb. If that ship contacts the dock at even fraction more than planned speed, the damage is catastrophic. We are talking about crumpled steel, destroyed dock infrastructure, vessel that can cost $300 million. The job of a tugboat on the far side of the ship, between the ship and the dock, is not to push. It is to squeeze, to resist the inward drift, to act as shock absorber and brake, using its own engines against the momentum of the ship to slow the final approach to almost nothing. That tug is pushing outward against the hull while the ship is drifting inward. The two forces meet in controlled collisions of physics. The result is 200,000 ton ship coming to rest against a dock at something close to a gentle lean rather than an impact. All of that happens in an while an arbor pilot coordinating the tug captains by radio, while currents shifts beneath the hull, while the wind pushes against 40 meters of container stuck above the waterline. Now let's walk through the actual operation step by step in real time. The container ship has cut its main engines and it's coasting toward the port entrance at about 4 knots. 2 or 3 tugs are already in position. They meet the ship in open water outside the harbor mouth. The lead tug connects a tow line to the ship's bow, not to push it forward, but to control its heading. This prevents the bow from swinging too far in either direction as current catches it. A second tug position at the stern. Its job is rotation. When the harbor pilot calls for a ship's bow to swing to the port, the stern tug pushes to starboard. The ship pivots slowly like a needle on a compass, except the needle weighs 200,000 tons. As the ship enters the channel, the speed drops further. The tugs transition from escort mode into active positioning mode. Now the Z drives are working at angles, generating lateral force to keep the hull centered in the channel. Then comes the final approach to the berth. The ship is barely moving. The bow tug holds the lines tight. The stern tug angle its thrust to manage the drift. The tug on the dockside, the brake tug, pushes outward against the hull, measuring the approach meter by meter. The harbor pilot issues a final command. Tugs push and the ship is against the original dock lines are thrown. The ship is fast. The entire operation from the moment the tugs made contact in the water. And in all that time, not one moment of that process was accidental. Every push, every angle, every transition between thrust directions calculated by captains, harbor experienced, who understand the physics of enormous objects in the confined spaces better than almost anyone alive. The tugboat is not simple machine. It is most maneuverable working vessel in any harbor. The reason those massive ships don't get in and out port safely every single day without accident is almost entirely because of them. To me, that is where the real beauty of this story lives. Not in the size of the ships, but in the fact that the most critical moment in a 200,000-ton voyage is controlled by a machine that weighs 300 tons and looks like floating shoebox. But physics don't care about size. It only cares about force, timing, and direction. And now I'm curious, have you ever wondered that why actually when ship goes wrong in a harbor, and how ports engineered to survive a collision with a vessel that massive? I've already started working on that one. Subscribe so do not miss it.